All right, thanks for coming by our lunch seminar. Today we have Ethan Coffel. He's a third year graduate student in the Department of Earth and Environmental Sciences at Columbia, and he's a student with Radley Horton. He'll be speaking to us today about heat stress and other climate change impacts. So please,
right.
Ethan.
Great, thanks. So we've been working on this project for a little while about population exposure to heat stress with Alex Sherbin from CSUN up at Lamont. So there's been a lot of work about climate change and heat in recent years and temperature extremes. Most of it has focused mainly on temperature itself and how temperature extremes may change. There have only been a few studies, though, that have incorporated humidity. But as I think everybody knows, humidity is just as big, if not a bigger, component to both the level of discomfort and danger of extreme heat events. And so some recent examples have made that clear. In Chicago in 1995, there was a heat wave that killed in the range of 700 or 800 people. Then in Europe in 2003, there was a very large heat wave that covered most of Western Europe and was estimated to have killed 70,000 people. And then in Russia in 2010, there was a similar heat wave which was estimated to kill several tens of thousands of people and also significantly decreased their crop yields that year, and I believe resulted in them banning their wheat exports. And I also believe that was tied to an increase in global food prices the following year. Then this year, there was a heat wave in India and Pakistan, which made the news, killed a couple thousand people there, but there were also a couple of notable single temperature measurements related to this heat wave. Specifically, there was one in southwestern Iran, where there was an air temperature of about 122 Fahrenheit and a dew point of 90 Fahrenheit. This resulted in a heat index value of 165. It's not the hottest ever recorded, but it's up there. The hottest, I believe, that was about a decade ago in Saudi Arabia, where there was a heat index of 178. So those are sort of unbelievably high and probably unlivable conditions. So there are some common indicators that are used for heat stress as opposed to temperature. So the heat index is probably the most well-known. It's reported in the US weather forecasts. It's based on an empirical formula that makes some assumptions about human response to heat, and it's entirely based on temperature and relative humidity. There's the wet bulb globe temperature, which has a long history of use for predicting heat illness in the military and industry and in athletics. And so this is a weighted average of the dry bulb temperature, the regular air temperature, the wet bulb temperature, and also a globe temperature, which is measured by putting a thermometer inside of a black globe. And that's not a standard instrument, and it's not reported in normal sort of weather stations. And so that index is not available, and it's also not that easy to calculate or model based on standard meteorological measurements. So in this study, we choose to look at the wet bulb temperature, which is easier to work with and more sort of physically based than the heat index. So the wet bulb temperature is measured by taking a thermometer and putting a wet cloth over the bulb, and you read off the equilibrium temperature. And so the difference between the wet bulb temperature and the air temperature is the result of evaporative cooling. And so it's really a measure of the efficiency or the rate of evaporation. So this is also how your body's cooling system works. You produce sweat and it has to evaporate. And if the evaporation slows down or is impeded for some reason, then you will not cool off as quickly. So as the relative humidity increases, the evaporation rate goes down, and so the wet bulb temperature goes up, and you stop cooling yourself as efficiently. And at some level, you lose the ability to cool yourself at all. So we calculated the wet bulb temperature using relative humidity and air temperature using an empirical model from was published in 2011 and was shown to work pretty well, and it's pretty easy to work with. So in 2010, there was a paper by Sherwood and Huber that they went through and tried to calculate an absolute limit of wet bulb temperature for human tolerance. So the limit at which you totally lose the ability to cool yourself. And so you will experience heat illness without some sort of artificial cooling. they found this limit to be 35°C. And this limit has, it's not commonly reached. In most of these heat waves, like in Europe and in Russia and in Chicago, the maximum wet bulb temperature was in the range of 29 to 30. That single reading in Iran this year was just under 35. It was probably like 34.5 in that range. And then the reading in Saudi Arabia, I think, is the only known time when 35°C has been exceeded. I believe it was like 35.4. Of course, those were not particularly populated areas that those occurred in, so we really don't know what happens to large groups of people when this threshold is exceeded. But so that 35°C threshold assumes sort of optimal cooling conditions. So a person in pretty good shape, basically like sitting in the shade and wet and having some air movement. So under realistic conditions for someone who, say, is like working and probably wearing clothing while they're doing that, the limit is probably much lower. So perhaps 1 to 2 degrees C lower for like the absolute limit of what people could tolerate. So in this study, we aim to project the population exposure to extreme heat stress levels. And so to do that, we need some population data. And we took our data from the SSPs, or the shared socioeconomic pathways, which are sort of plausible scenarios of economic and social, sort of economic, social, and demographic change in the next century. So these are, I think they have a lot of they have a set of data that's economic projections or economic scenarios, but they also have a population component. And there's 5 scenarios, and they're sort of loosely tied to the RCPs, the emission scenarios used in CMIP5 experiments. And so they're presented in very fine scale gridded data, 14-kilometer grids for each decade in the 21st century. So there are 2 scenarios that correspond to RCP 8.5, and so we chose the scenario SSP5, which is not the worst case scenario, but like reasonably bad. So it's described as a low mitigation, high adaptation scenario. So where there's rapid technological change, rapid economic growth, but also rapid emissions growth, but a decrease in inequality, and so probably an increase in adaptive capacity in a lot of the world. The other scenario that corresponds to 8.5 is SSP3, which is sort of low mitigation and low adaptation. So that's rapid economic growth, rapid population growth, and increasing inequality, and presumably lower adaptive capacity in a lot of the world. So the base population projections in 2020 in SSP5 are a world of about 7.5 billion people, a little bit more than there are now. And most of the population, of course, is in a couple of regions. So in Africa, West Africa, Central Africa, India, and China. And most of the rest of the world barely even shows up. So there's some areas in Europe that are densely populated enough, but and some of the eastern U.S., but it's nothing compared to the densities in India and China especially. The right side is the projected population in 2060 according to this scenario. And so we see the world gains about 1 billion people, and almost all of that increases in a couple of regions. So in West Africa and in India, and then in the Middle East. And that increase is enough to balance out a significant decrease in eastern China, where China is predicted to lose maybe 100 or 200 million people. So there's some increase in the eastern U.S., which sort of surprisingly even shows up on this map, and there's increase, of course, in like South America and in other parts of Africa, but it's so small. It's of a different order of magnitude, really, than the increase in West Africa and in India. And I guess, unfortunately, these regions with the fastest growth are also the hottest places in the world, and projected to see the most rapid increases in heat stress. So we want to project the wet bulb temperature in the future, and we're most interested in the daily maximum wet bulb temperature as a measure of sort of maximum heat stress that will be experienced. So the climate models and the reanalysis data generally provide the daily mean, relative humidity, or the 3-hourly values. We chose to calculate the relative humidity at the time of highest temperature using the specific humidity, the daily mean specific humidity, the daily mean sea level pressure, and then also the daily maximum temperature. So we did this because if you take the daily mean relative humidity, that's not good because it, of course, responds to temperature. And you'll probably get an answer that's like a heat stress value that's too high. And the 3 hourly data we are planning to probably use in the future to sort of check this result. But we think that if anything, this probably underestimates heat stress because looking at the relative humidity at the time of highest temperature probably gives a relative humidity value that's a bit too low. In many heat waves, the time of highest heat stress has been seen to occur both before the highest temperature, so usually like sort of in the late morning, when humidity is declining as temperature increases, and there's sort of a balance of whether the increasing temperature increases heat stress enough to counteract the decrease in heat stress that comes from declining relative humidity. So we think these are probably like slightly conservative relative humidity estimates or heat stress estimates. But so when we do this calculation with each CMIP5 model and then the NCEP2 reanalysis, they do at least align pretty well, especially in the regions that we're interested in. So in West Africa, sort of India, especially Northeast India. And most of the differences are in regions with terrain, like in South America in particular. So the CMIP5 models, of course, have biases, and since we're interested in looking at sort of these absolute wet bulb thresholds, the biases are important. So for temperature, this is the bias in the multi-model mean bias in the annual maximum temperature, so the single highest temperature in a year. So these biases are in the range of, like the highest bias you see is about 5 degrees Celsius. And they vary quite a bit spatially. For wet bulb temperature, annual maximum wet bulb temperature, the biases are lower. That's, I think, because there's lower variability in wet bulb temperature in the first place, and also there's a paper by Fisher and Newty, I think in 2012, that they looked at the uncertainty present in variables like heat stress that are dependent on two sort of fundamental variables, so temperature and humidity, and they found that the uncertainty declines in those variables when they're sort of linked. And so there might be some of that going on here. But so we applied a bias correction to this data so that we can look at these absolute values. And we used a pretty simple scheme where we divided the temperature distribution in each model and in the reanalysis up into 10 percentile bins. So we took like each temperature between, say, the 0 percentile and the 10th percentile and then the 10 to 20. And in each one of those bins, we calculated the mean bias between the model and the observations and corrected that. And so we did this instead of, say, correcting the mean bias over the whole distribution because we find that the biases are quite different when you get to sort of the tails. So the high tail of the distribution versus, say, the middle, you get a different bias. And so since we're interested really in the top of the distribution, we needed to do a bit better than just looking at the mean. So when we apply this bias correction to the mean daily maximum temperature, so these are like the high temperatures on each day, the biases are reduced from in the range of 5 degrees to, in most places, under 1 degree. So if you look at the biases at the very top of the distribution, they're still, they're bigger than this, but this method does seem to perform pretty well and still have a large enough sample size in each bin to be reasonable. So we project temperature using these 11 chosen CMIP5 models under RCP 8.5. And so these plots show the projected change in the annual maximum temperature and the annual maximum wet bulb temperature in 2050 to 2070 relative to the base period of 1985 to 2005. So increase of temperature 3 to 5 degrees C, increase of wet bulb temperature of 1.5 to 3 degrees C. And so the increases are like pretty spatially homogeneous. There's variation, but it's in the range of 1 to 2 degrees C. Of course, if we chose a different RCP, these values would be lower.
This is maximum mean.
Yeah, and this is the annual maximum. So these increases are larger than if you looked at the daily mean maximum, and they're larger than if you looked at, say, the annual average. So one way to think about increases in heat stress is looking at the actual temperatures that might be reached in the future, but another way is to look at how often current extremes occur in the future. And so we looked at the recurrence values of temperature and wet bulb temperature. And so we defined the recurrence as the number of days in the future that exceed the annual maximum temperature in the base period. So here we do this for the 2060s. And so on the left is the annual maximum temperature in the base period from the bias-corrected Zeeman-5 models. So these are, I mean, the highest values you get approach 50 C in the Middle East. These line up pretty well if you look at the unset values. And then on the right is the projected recurrence, so the mean number of days per year that exceed this value, at least like at any point during the day. So you see pretty large increases, especially in the tropics, and of course they're larger in the tropics because of the decreased variability. So in like northern South America, you see increases of like 80 to 100, or well, you see 80 to 100 days per year that exceed this annual maximum in the past. And in the Middle East, similar values. But even in some mid-latitude regions, like in the U.S., in the west, we see values of 30 to 40 days. And even in the Northeast, like New York, 10 to 20. So that's quite a few days that exceed the current annual maximum. It's, you know, a very different summer. So we do the same thing for wet bulb temperature, and these results are more dramatic, probably because of the reduced variability in wet bulb temperature, especially in the tropics. So in the past, or in the base period, the annual max wet bulb temperatures are basically in the range of 28 to 30, maybe 31 in some places, but they never exceed 31, at least in this sort of this mean annual max. There's like the observation of 34 and 35 in Saudi Arabia and Iran, I think, are, well, it's the only time they've been observed, so perhaps those occur very rarely, but they don't show up here. So in northern India, probably has the highest values in the world, perhaps approaching 32 currently. And then when we project this in the future, you see the whole belt of the tropics is projected to see more than 100 days that exceed this value. And you go up into the mid-latitudes and you also have pretty significant increases where in the US, well, so here we zoom in on a couple of regions. And so like, look in India, so the west coast of India sees significant increases of almost 150 days that exceed the base period annual max in some of these grid boxes, and similar in Bangladesh and Myanmar, and this continues down through Southeast Asia. In the U.S. Southeast, like in the range of 60 days, something like that, perhaps a bit more in the Gulf Coast. And then in the Northeast, we project in the 30 to 40 day range. So those are quite significant increases, especially since basically the base period wet bulb temperatures in the U.S. In the range of 28 in most places, and so the heat wave in Chicago had a maximum wet bulb temperature about 29.4. So saying that if you have 30 days that exceed that, that's a whole month that approaches the levels that we're seeing in one of the most severe heat waves we've had in recent history. So West Africa has the highest changes in the coast of West Africa, 200 or more days per year. And I think this is mostly due to the low variability of wet bulb in this region, because they actually don't see the actual values are not as high as they are in India or Southeast Asia, even in the future. So when we project this into the future, these are the mean annual, or the annual mean maximum wet bulb temperatures. So in India, this is the hottest, this is the region that sees the highest values of 32, perhaps 33 in some places. And then also in China, you see quite high values in sort of the interior of in the 32 range. In the US, projected values of 29 to 30. So using these projections, we can then go and project population exposure to these levels using the SSP population data. We do this regionally and then also globally. So for the regional projections, we choose 31C because that's sort of the base period limit of wet bulb temperature. And we do this each decade. So these are the decadal averages and also the averages. So it's done for each model, and then we take the multi-model mean. So for the US Northeast, projected exposure in the 2060s in the range of 30 million. That's an increase from basically 0 now because this temperature doesn't really occur here. In India, an increase of 5-fold, and an increase of 10-fold in China, and an increase an increase from very low values now in West Africa. So some of this increase comes from increasing temperature, some of it comes from increasing population. And we break that down when we look at the global projections. So these are projected exposure to 32 and 33C. We break it down into 3 components. So the sort of component that comes from rising populations, and so this is calculated using the population data but a constant climate. And in many, well, actually for both of these, it's basically 0 because these values don't occur in the current climate for the most part. And then the sort of effect that comes only from rising temperatures is calculated by using the 2020 populations but a changing climate. And this is the vast majority of the effect. And then there's sort of a third effect that comes from increasing population and increasing temperatures. And that ends up, it's a significant but smaller component of the total. So if you look at 32C, the projected exposure is in the range of 700 million by the 2060s, and 600 million of that comes from the changing temperatures, and the rest comes from sort of this interaction between temperature and population. And 33C projected is in the range of 250, with 200 of that coming from the changing climate and 50 from the interaction. So of course there's significant uncertainty in these estimates that come from, well, the uncertainty comes from, first of all, the climate uncertainty. We could not take the RCP 8.5 trajectory. There's also intermodal variability in this. There's uncertainty in the SSP scenarios. Population estimates have changed quite a bit between sort of in different projections, and so it's possible that population increase more or less than assumed in SSP 5. But our goal here is sort of to give an order of magnitude estimate of exposure, and sort of our results suggest that there's going to be large portions of the world and the most densely populated portions of the world exposed to extremely high heat stress values. So we looked at 32 and 33 here. We also did look at 34. There's a small portion, a small exposure, maybe in the 50 million range to that, and a smaller exposure to 35C. But we think that these values, probably under sort of operational conditions of somebody like doing something other than sitting in the shade, are going to be quite problematic. So bottom line is that by the 2060s, we expect significant exposure to wet bulb temperatures that approach the absolute threshold of human tolerance. And basically the hottest heat waves that occur now will become the normal summer in the future. And in many regions of the world, heat stress alone it's probably going to make outdoor activity difficult in the hottest parts of the year. And these effects also occur in usually the regions of the world with the least adaptive capacity. And so this is an impact of climate change that's worth considering, even alongside all the other potential problems.
Any questions or comments for Ethan?
Great job. I thought it was really cool. I was wondering, so you talk about your bias correction for the CMIT models, and I was wondering, I'm sure you saw Jeremy Powell's paper that just came out where they use a high resolution simulation, and I'm wondering what you think the effects of increasing spatial resolution would have on, say, something like wet bulb temperatures, right? So, if you looked at your map of the continental United States, California, I guess it was a projected population exposure map. There was one where California kind of pops up as
occurrence
red. Yeah, maybe it was the occurrence, right?
Yeah.
And for estimates like these, getting topography right, and therefore kind of advection and circulation better. I'm just wondering what your thoughts are on kind of
well, actually,
this issue with resolution.
I was thinking about that specifically in terms of the Middle East, because basically in these projections, the Middle East has, so this is the, okay, maybe it's not on here, but if you look at the projected wet bulb temperatures for the Middle East, like you see high values, but they're in the 31 to 32 range. Whereas I think this recent paper was saying that like coastal cities in the Middle East could experience temperatures exceeding 35. And so both of those observations of the wet bulbs approaching 35 were in these coastal cities in the Middle East. And so I think not picking it up in this 2-degree grid is that's why probably if you could do it with increased resolution and still model it well, you might be able to get that. And so that would definitely be important for the regions with coastal cities, especially where the presence of the water makes a big difference.
Well, and also which is co-located with greatest population densities in most of the developing world. So,
And I think a little bit of elevation difference can matter quite a bit, it seems like. So there's that element, but then also maybe there are some really fine spatial scales. Maybe there are some features in terms of you'd want to look at sort of daily circulations during the day, affecting some of that warm water. And I think another interesting piece is maybe anything we could do to sort of improve projections of SSTs, near coastal SSTs is obviously an enormous problem, but those could be a big driver. Any changes in coastal upwelling, for example, those kind of things could have a big impact on these results.
There's also a strong diurnal cycle of temperature near the coast when you have a sea breeze coming in the morning. So you talked earlier about how you have rising temperatures early in the day. At the same time, the humidity might be decreasing, and so that's something where these coastal cities might be a place where you really want to look at more time resolution.
Yeah, and I think we can look at, I think in the future we'll look at the 3-hourly values of relative humidity and temperature, and you could fit a curve to that and see how it changes in different cities and come up with better estimates of the maximum and also sort of the time spent above certain thresholds. But I guess again, higher resolution would be useful for that.
You're going to want to resolve essentially the onshore flow every day.
Yeah.
That'd be useful.
How about like a related question of boundary layer issues? I mean, when you mentioned late morning too, I got to wondering if that's a time of day where you're starting to get instability from the sunlight hitting the ground. I don't know if the humidity tends to be stacked near the surface in a way that there might be some lateral issues. There might be some interesting vertical issues getting involved late morning, early afternoon. I don't know.
You might have more ventilation. So if you look at the evaporation formula, there's a term out front which measures like the wind speed and essentially how vigorous the mixing is, and that might be something that goes up in the middle of the morning. That might affect some of these estimates of like what's the maximum tolerable wet bulb temperature that humans can take.
Yeah.
Sometimes that might be maybe something you could do is go back and look at some of these estimates, like how when they say 35 degrees Celsius, is that based on some assumed ventilation, or you can use projections of future ventilation, or even like the diurnal cycle of ventilation today to see if maybe if some of these higher temperatures and higher wet bulb temperatures in the middle of the day might be more tolerable just because there's more convective boundary layer mixing, like gravity says.
think in that paper they assume like a sort of low wind speed, some value. Like,
Right.
I don't know, but
That's probably appropriate for like 6 in the morning.
yeah.
But,
Yeah, because I think at least in the Chicago heat wave, I think the maximum heat stress occurred usually like around like 11 a.m.
yeah.
So.
Okay.
Are there any land cover changes in the model, like accompanying population expansion? Mostly for like suburban to urban.
I don't know. Do you know, Justin, if they have that? SSPs?
As part of the SSPs, are they, I mean, certainly the population is considering kind of urbanization effects, but in terms of like surface albedo changes, and things like that, I think, it depends on what CMIP models you would be using for, vegetation changes might be incorporated and things like that, but I don't think like city albedo changes would be occurring, but I'm not sure.
Because in these population projections, you'd see some huge cities forming.
Yeah.
Unprecedented cities all over.
Yeah.
That's going from 10 million to 30 million.
That's most of the increases.
So you could imagine if someone wanted to say use WRF in their long-term graduate work, if this was interesting, you could imagine maybe sort of building in a piece where you change the lower boundary condition,
Yeah.
for sort of internally consistent pieces with the SSPs and see what that might do. But more generally, it suggests at least potential for high resolution modeling, capturing some of those lateral and vertical motions.
Yeah, I mean that's one of the problems with the kind of loosely mapping SSPs onto RCPs and just kind of having incongruent visions of the future, right? It's just doesn't totally make sense, but it's important to kind of try to reconcile where you can. Do you have a sense of what kind of the range of ensemble variability in these? Because you've shown only mean estimates.
Yeah, that's actually something that's sort of in progress. So I don't really have a number, but that'll be in the paper.
Comments, questions?
I mean, for me, like one of the interesting things you brought up earlier is just the diurnal cycle. Maybe because it seems like right now people are making these fairly gross indices to maybe looking at the maximum during the day, and you maybe use like high resolution model data, like maybe looking at a city or something like Los Angeles where you have this sea breeze that penetrates a certain amount of distance, and where you could actually look and see how much how much does the ventilation change, and what's the different effect of the temperature versus the humidity, and how these things play off during the day. I think that sounds like there's a lot of unexplored territory there.
Yeah, because I think the high values, like, they occur. You have to be at that right sort of trade-off between temperature and humidity.
Yeah.
So yeah, definitely, that'd be interesting to do.
For the map that you showed near the beginning with relative humidity at the time of maximum temperature, how is that? I didn't catch. Is that just calculated like from hourly station, the NSEP? Hourly station data?
So we took the daily mean specific humidity and the daily mean sea level pressure, and then the daily maximum temperature, and from that you can calculate relative humidity. And so that was our sort of relative humidity value at the time of highest temperature.
Assuming the specific humidity is.
Yeah, because at least it doesn't vary with temperature. So we assume it's more reasonable to use the daily mean, but definitely would be good to look at the 3 hourly values and sort of how it. Because if you did that and you could fit a curve to the sort of change in heat stress and estimate the real daily maximum.
Well, because sort of what we're talking about, the wet bulb kind of calculated from these two values might not be as high as the actual max wet bulb.
Yes, it's assuming the maximum occurs before the time of highest temperature. Because if the temperature is higher, the relative humidity will be lower, and it'll change the wet bulb temperature. It's sort of unknown whether it will increase or decrease it. It depends.
There's Dan Horton, who's at Northwestern now. air stagnation events in the future with the CMIP-5. And one of the things that he did was, given that he was calculating, the NCDC's air stagnation index, which is a combination of a bunch of different meteorological variables, he kind of pulled an ensemble of observations and did different permutations of, of wind speed and surface temperature and kind of vertical profile, and had a range of observational values that he then mapped onto each of the CMIP-5 projections to kind of create a super ensemble of 90 projections of, giving a really amazing range of potential outcomes.
Yeah. Yeah, I mean, you could, assuming you have good observations of relative humidity and temperature.
Yeah, well, I mean, one of the embedded assumptions in that is that we don't have great ones, so why not kind of take them all and take all of their linear combinations and see how that changes the answer.
Did you look at nighttime stuff?
No, but yeah, I mean, so like nighttime temperature has a big impact on like health impacts. Sort of our goal here was to look specifically at, at these absolute thresholds of wet bulb. So I at least don't know of anything that's looked at the impacts of sort of sustained wet bulb temperatures at night, and whether that is as strongly related as sort of sustained temperatures at night. But
definitely a future work area that we wanna look at. There's some people at Columbia who've, I think, done a fair amount of work comparing high daytime and high nighttime temperatures in terms of the sort of mortality relationships. But my sense is there's more to do on wet bulb.
yeah, there hasn't been that much with humidity at all, and sort of mortality or.
I imagine the relationships are kind of similar.
I think that's.
Wet bulb makes it worse.
Yeah, I think most of them though have looked at specific places where maybe you don't have too many days that are hot but not humid, so you can't really separate the influence of temperature and humidity. So it might be interesting to look at, find a place that has heat waves that sometimes are dry and sometimes are humid, and see which one has bigger health impacts.
Yeah.
I mean, day-night is interesting because you have big contrast in ventilation in the sense that at nighttime you don't really have the stirring, by the convection. At the same time, you may have a lot of, as we know, living in the city, you may have a lot of residual heat storage. So the buildings may stay really warm in spite of the fact that maybe the air on the rooftop is cooling off a lot.
Yeah. Yeah.
So I mean, that's something that may change the perception of the heat, even if some of these canonical diagnostics like the wet bulb temperature are seemingly benign.
Yeah. Yeah, because I think it's either the biggest or close to the biggest determinant of heat deaths is from the nighttime temperatures. If you have a daily mean that's above a certain level, it starts to have a big impact.
Any other questions, comments for Ethan? All right, thank you, Ethan. Thank you, everyone, for your discussion, for coming by the seminar.